Hello everyone. Today I'm going to introduce a paper, and its title is the CPU scheduling algorithm, a comprehensive survey and the adaptive deadline-based approach. This research explores how modern systems can better manage task scheduling in increasingly complex environments. The author begin by highlighting that in our current era of cloud and IoT, resource allocation is no longer just about speed, but about handling real-time constraints and fairness. This sets the strategy for why traditional scheduling needs a more adaptive successor. Building on this motivation, the paper identified a critical conflict. Existing algorithms often fail to balance the real-time requirement with process fairness. This imbalance frequently leads to delay in critical tasks. So critical task or inefficiency in overall system performance. To address this issue, the researcher defined three core objectives. The first one is to optimize resource utilization, and the second is to ensure strict deadline awareness for time-sensitive tasks. And the third one is the fairness to maintain a balanced, responsive for all hours processed. Before proposing a solution, the author clarified the metrics used to measure the success. They define key terms such as arrive time, and which means the moment the process enters the ready queue. And the burst time is the total execution time required by the process. And the completion time, which the process finish and terminate. So they still talk about the R metrics, like the turnaround time. Turnaround time is the time when the process arrive to process and finish this interval. And the wait time. Wait time is the important one, which means that how long the process stay at the red queue. And so we'll know this formula, like the WT equals to the turnaround time minus the burst time. And our important things is the CPU utilization. And we want it as high as possible. And because we don't want the CPU be idle, because the idle CPU is useless for us, and the response time. But totally, the goal of this is to compress the wait time segment to improve the overall turnaround time. It's which thing is what we want. Right? And reviewing with this metric in mind, the paper categorized the current landscape into the three groups, which have the classic one, like the FC, FS, and SJN, and the advanced one, MLFQ, and the authors propose one, the novel one, ADBS approach, which focus on adaptive priority assignment. And we gonna reviewing the classic one and talk about its advance and disadvance, and how the ADBS to be the conquers their disadvantage. So between the classic, the paper note that the FCFS, which means that the first come first servers is a simple one and easy to implementation, but it suffers from the convey effect. Mean long process will block short one and will cause the short process wait time very large, and it's not very good for our process. And meanwhile, is the SJN, which means which full name is short test job next. It's optimal for reducing average wait time, but it's often impractical because we have to know the execution time before we schedule it, and it's costs a lot of resource to calculate it, and it's not very practical in for our dynamic environment in the matter mentioned, and it will cost very large, and it's kind of impossible for us to know that the execution time by in advance. So moving to more interactive method, which is scheduling way. The priority scheduling is very good. It's vital for critical tasks, but it will cause a serious problem called starvation. But starvation means how low priority will never be executed if the high priority keep coming. So it's very, very dangerous for our system. And the next one is the round robin. Round robin offer a fairness through time slice, yet its risk high overhead if the time quantum is not managed correctly, because it will content switch very often. So it will cost very large resource at the content switch, frequency content switching. And to solve this limitation, the author introduced the ADBS approach. And its heart is a dynamic prior function. It's the PI of T, which adapt based on its absolute deadline D, and the remain time R, and the current system utilization U, and the worst case execution time. This ensure the priority involved as time passed. And it will continually change the priority by this parameter. And structurally, ADBS is built on 4 key pillars. The deadline specification, priority assignment, unslicing, and the load balance. This integral logic allows the system to remain responsive even under heavy load. The paper detail the specific algorithm, which means the pseudocode for priority assignment. And a pseudocode is continuously loops through the task to calculate relative urgency, ensure that as a task near its deadline, it's moved to the front of the queue. And furthermore, the research implement, sorry about that. Implement dynamic time slicing, where high priority tasks receive longer execution block, and a load balance mechanism to prevent processor bottleneck in multi-core system. And to validate the approach, the authors simulate a workload where all 5 processes, P1 to P5, arrive simultaneously at time 0. They compare 2 scenarios, which at the table 2 and table 3. The table 2 use the fixed 5 millisecond time slice for all tasks. And the scenario B is the table 3, ADBS with dynamic time slicing. Is applied where time quantum are assigned based on priority. Give the high priority 50 millisecond, medium 10 millisecond, and the low priority test 5 millisecond. And the result was significant. The ADBS turnaround time is lower by it. It's from the fixed time slicing is 35 millisecond, but the ADBS one is 25 millisecond, and it's reduced. The turnaround time for a critical test is reduced by 28.5%, and it's kind of important for us. Let us know that the ADBS one is totally useful for us to reduce the wait time and comprehend the turnaround time. And the paper concludes that ADBS offer the superior scalability for platform like IoT and the multi-core server. However, the author honestly notes a limitation: the constant recalculation of deadlines increase computation overhead. In summary, this research successfully demonstrates a way to balance urgency and fairness. Future challenges involve optimizing the overhead to make this suitable for even smaller, low-power device. And thank you for your attention. This is my presentation for the ADBS scheduling report.